A man starts walking north at 4 feet per second from a point P. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of point P. At what rate are the people moving apart 15 minutes after the woman starts walking? So for any related rate problem, I always want to begin by drawing a diagram. So we'll start with the man who is starting at point P and walking north. I also like to indicate the direction of travel, so I'm going to indicate that with arrows. So there's my man walking north. And then 5 minutes later, it says a woman starts walking south at 5 feet per second from a point that is 500 feet due east of point P. So since I'm going to have to be due east, let me relabel point P over here. So from a point 500 feet due east, here's where the woman begins walking, and she's going to walk south. The woman walks south. So I want to label my diagram, but I need to be sure that I am being very careful with the quantities that are changing and the quantities that are remaining constant. For example, the man who is walking north, as he walks north here, his distance from point P is changing. Therefore, I would want to go ahead and give that distance a variable name. So I'm going to use M to represent the distance that the man has walked north. And along those same lines, the woman who is walking south, her distance from the point where she began is changing as well. Therefore, I'll use W to represent the distance that the woman has walked south. However, the distance between the 2 points where the man and woman begin walking, that distance does not change, and that distance stays 500 feet. So you never want to put a number on your diagram if that quantity is changing. I always recommend that you think about what's changing, those will be variables, and what is remaining constant. Now, we also want to search for any rates that were given to us in this problem. And we were given 2 rates. The rate at which the man was walking north and the rate at which the woman was walking south. I don't recommend that you put the rates on your diagram, but rather put the rates off to the side, and we'll want to label those. Our first rate was 4 feet per second, and that was the man's rate. So therefore, that would be labeled as dm over dt. The second rate was the rate at which the woman was walking, which is 5 feet per second. So that would be the rate at which w is changing. So that would be labeled dw dt. And lastly, we want to come up with what I call a find statement. So what are we being asked to find? And in this case, we're finding at what rate the people are moving apart. So going back to my diagram, we need to label the distance between the 2 people. So if the man ends up walking at a point up here and a woman ends up walking at a point down here, then the distance between them would be indicated by this red line segment. That length is also changing, so I would use another variable here. You can use any variable you want. How about maybe z? So the distance between the man and the woman at any given time would be z, so the rate at which the people are moving apart would be labeled dz over dt. So we want to find dz dt 15 minutes after the woman starts walking. So I'll just label it exactly like that, 15 minutes after the woman begins walking. And this is what I consider the setup for a related rates problem. A label diagram, we have our rates labeled and indicated, and we have a good find statement, is what I call it, what we're trying to find. So next we're going to try to come up with an equation that relates our variables as well as our constants. So in this situation we have m for a variable, we have w, we also have z, and then we have this constant of 500. So we're searching for an equation that relates all of these quantities. Now, when you initially look at this diagram, you might make the mistake and think that you have two congruent triangles, because I do see that we have two right triangles here, and the way I have this drawn, it kind of looks like these two triangles are congruent. But you have to be careful because remember, the man is walking at a different rate than the woman, so these two lengths are not going to be the same. So these are not necessarily going to be congruent triangles. In addition, the congruent triangles would not involve the length z, and we are looking for an equation that would involve the relationship between m and w as well as z. So we are not going to use congruent triangles in this case. And we'd also like to look at the 500 and find a way to use the 500 feet, which was the distance between where the man and the woman began. So notice, if I drop down a little bit and look at where the woman ends, if I were to draw that horizontal distance in, this would also be a distance of 500. So if I were to come straight down from point P and create a right angle here, then I've essentially created a larger right triangle, and the base of this right triangle is 500, and the hypotenuse of this triangle is that value of z. Let me do that better for you. The hypotenuse of this right triangle is the distance between the man and the woman, which we had previously labeled as z. So looking at this triangle drawn alone, I have a hypotenuse of z and I have a base of 500. So now we just need to think about what the height of this triangle would be. Going back to my diagram, from point P up to the top of this triangle, that was the distance that the man has walked. But notice from point P down to the base of this triangle, that line segment would be equivalent to the distance that the woman has walked south. So we could label that as W. Therefore, the entire length would be M plus W. So now we have a good right triangle with all three sides labeled. So the relationship between the three sides of a right triangle will be Pythagorean theorem. The base, which is 500 squared, plus the height of this triangle, which is m plus w squared, is equal to the hypotenuse squared, which would be z squared. Now at this point, I would pause before you jump ahead and go to the derivative. We want to pause and make sure that we would like to actually keep all of these variables. We have three variables altogether here in this equation, and we need to decide, should we keep all of them, or do we need to eliminate one of these variables? The key is to look at the rates that we know and the rates that we're looking for. So in this equation, I would recommend we're going to keep the variable m because we know the rate of m. We know dm dt. We're going to keep the variable w because we know the rate dw dt. And we're going to keep the variable z because if we look at what we're trying to find dz dt. So this is a situation where we will actually keep all three variables. So we are ready to go ahead and take the derivative. We are using implicit differentiation, where we are going to take the derivative of both sides with respect to time. So I'm taking the derivative of 500 squared with respect to time, plus the derivative of the quantity m plus w squared with respect to time, and the derivative of z squared with respect to time. So 500 squared is a constant, so the derivative of a constant will just be 0. However, m plus w squared is a composite function, so we'll need to use the chain rule. So the derivative there would be 2 times the quantity m plus w, And then chain rule requires us to chain on the derivative of m with respect to time, which would be dm dt, plus the derivative of w with respect to time, which would be dw dt. And the derivative of z squared would be 2z dz dt. Now notice we have the value here for dm dt, which was 4 feet per second. We also have dw dt, which was 5 feet per second. But we do not have the value of m or the value of w. So we need to go back to the problem and reread. And notice we were interested in what was happening 15 minutes after the woman began walking. So the woman is going to be walking for 15 minutes. So let's go back and off to the side, let's think about the woman. She is going to be walking for 15 minutes. And then let's think about the rate at which she was walking. So dw dt was 5 feet per second. So for 15 minutes, but she's walking 5 feet per second. So we need to go ahead and convert. So 15 minutes, we'll go ahead and say that there are 60 seconds in each minute. So 50 seconds in 1 minute means that the woman will have walked for a total of 900 seconds. So 900 seconds and the rate that she was walking, which was 5 feet per second, will give us the distance that she will have walked. So thinking about it this way, we see that she has walked 4,500 feet. So W, the distance that the woman has walked, will be 4,500. Now we need to do the same thing for the man. But remember, that requires us to go back and reread the problem. It said that the man starts walking first, and then 5 minutes later, the woman starts walking. So if the woman has walked for 15 minutes, the man has walked for 5 minutes more than her. So the man will have walked for 20 minutes. So for the man, we're looking at walking for 20 minutes. We'll convert minutes to seconds again. So 60 seconds in 1 minute. So the man will have walked for a total of 1,200 seconds. So 1,200 seconds, and we'll multiply that time by his rate. And the man was walking at a rate of 4 feet per second, which gives us a final distance of 4,800 feet. So the man's distance, or m in this case, would be 4,800. So now we have the value of w and the value of m. So let me go back to my derivative. In my equation here, we have the value of m, which was 4,800, plus the value of w, which was 4,500, times dm dt, that was the man's rate, which was 4 feet per second, plus the woman's rate, which was 5 feet per second. And now that's equal to 2 times z. So we realize, I have another quantity here that I don't know, multiplied by dz dt, which is what I'm looking for. So one final step here is to figure out what is the value of z when the man and the woman have both walked these distances. So if we go back one more time to our triangle, you'll notice I draw a lot of pictures here. We had the man that was walking north, and then 500 feet away, the woman was walking south. But we discovered we could go ahead and make this one large triangle, like so. So I can actually get rid of this quantity. Z was the distance between the man and the woman. And then we had discovered that if we had added these values, this would be M plus W. So the man's distance plus the woman's distance. 4,800 plus 4,500, 9,300. So the man plus the woman, their distances together equal 9,300, and remember the base of this triangle was 500. So we can use Pythagorean theorem to figure out the value of Z at this moment, 15 minutes after the woman starts walking. So 500 squared plus 9,300 squared is equal to Z squared. Use your calculator and compute this, but leave it exact so that we only round one time at the end of this problem. And this is the square root of a pretty large number, 8674000. So what is that? The square root of 86,740,000 is going to be the value for Z at that instant. So then we can go back, finally, back to our derivative. Now we have a value for Z at that instant, and that's what's going in here, the square root of that large number. So on the left-hand side here, we can go ahead and compute everything on the left. So 2 times 4,800 plus 4,500 times 4 plus 9. So that will give us 89,640. Oops, just kidding. I just made a calculator keystroke error. Type that again. That's going to be 16,000. One more time. 167,400. There it is. 167,400, which is equal to 2 times the square root of this huge number times dz over dt. So we can finish this sucker up by dividing by the 2 times the square root. So you can type all of this in our calculator and get an approximate answer here, which should be rounded to 2 decimal places, 8.99. And then we finish off with units. Remember, this is the rate at which Z was changing with respect to time, and Z was the distance between the man and the woman, which was measured in feet. So this is feet per second. And then it is a positive rate, which implies that the distance is increasing. So our final statement could be something like 15 minutes after the woman begins walking, the distance between the man and the woman is increasing at a rate of approximately 8.99 feet per second.